Hello, today I'm going to talk a little bit about stream restoration as a MS4 BMP. So in modern stormwater management, we're talking a lot about stream restoration, green infrastructure, nature-based solutions. You hear all these terms thrown around of things that are starting to be intertwined into our stormwater management. Hopefully the purpose of my presentation today is to think about how we can quantify things in terms of outcomes so that we can compare them to each other, such as how does stream restoration compare to an extended detention basin or a full spectrum detention or to a rain garden. So that's the purpose of my presentation today, and hopefully you'll have a better idea of how to do that and some of the literature and methods out there that have been approved by EPA and others to that allow us as practitioners to do this. So before I get into my presentation though about stream restoration, I want to ask everyone a question. Who owns a drill? That's a picture of my drill, the type of drill I own, a DeWalt. It's a really nice drill, has 2 speeds, variable speed, keyless chuck, pretty nice drill. But you know what? None of us need a drill. What we need is a hole. And actually, we really don't even need a hole. What we need is probably a bookshelf. And we don't need a bookshelf. What we need is to get our books off the floor and have a place to display them and show them. So this is an analogy that Seth Godin, that I stole from him, but I think the same can be true of stormwater, right? No one needs a dry detention basin, an extended detention basin, a full spectrum detention basin. No one needs a rain garden, a bioretention basin, a green roof. No one really needs stream restoration. What we need is safe communities, healthy communities, livable cities, where people can be safe and enjoy themselves. And really, we just also want to make sure people are happy. And one of the things I love about stream restoration and stormwater in general is we all get a chance to create happiness. And the reason we do this is because we work with water. And water, being in and around water, just generally makes people happier. This is a quote adapted from Blue Mine, which is a great book about by Dr. Nicholas Wallace about how water makes people happy. And the reason is that we were born in water and we know intuitively we need water to survive. So here's the quote from the book. We are naturally inspired, calmed, and just generally made happier by being on or around water, playing in it, walking next to it, hearing it, painting it, fishing in it, writing about it, and creating memories around it. So everyone at this conference creates happiness and joy for our community. But what we do when we talk about stormwater is we're starting to expand our toolbox, right? Here's a great toolbox, lots of good tools. We need more tools. We don't just need ponds, pipes, inlets, and stuff to get flooding away. We need more. And so we know we're starting to move to green infrastructure, and I'm sure there's lots of good presentations in this conference about green infrastructure. And we've gotten a good way to quantify green infrastructure, and certainly stream restoration is part of green infrastructure, but we don't really talk about it in those terms. You know, it's a nature-based solution, no different than a bioretention. And you can go to the International Stormwater BMP database, you know, it might be in a stormwater design criteria, and find a pollutant removal rate or input in load and input out in quantity or load. So how do we sort of bring stream restoration in there so we can compare it? And I'm going to talk about some case studies why it's important to be able to quantify the value of stream restoration from a pollutant and nutrient reduction, as well as you could quantify it in terms of flood reduction. So this isn't something new, right? This has been around since 2014, and a lot of this research goes to a lot of Tmdls. And the largest Tmdl in the United States is the Chesapeake Bay Tmdl, which involves 9 states, and it goes up to the mountains of West Virginia and New York State and down into the coastal plains of Virginia, Maryland, and into the Chesapeake Bay. So it's a variety of landscapes, a variety of urban, non-urban, and where this research has really come out of. And this original paper that I'm using a lot of, you know, was originally drafted in 2014. So the recommendations of the expert panel to divide removal rates for individual stream restoration projects. And then they've been working on improving the protocols, which I'll go through the 4 protocols over the last couple of years. So this is exciting stuff, but something not new. So there's 4 basic protocols when we talk about pollutant removal of stream restoration. And I'll go into depth in each one of those in a minute, but the 4 protocols involve preventing sediment. So that's not really pollutant removal, that's pollution prevention, right? So we're keeping erosion and sediment coming out of stream banks from moving downstream. And if you stop sediment, you're also reducing other nutrients that attach to sediment, such as nitrogen, phosphorus. And so the method is to define the bank retreat using a model. Banks is probably the most popular one. It's an EPA model. And then you measure the content in the stream banks. So this could be field measured, this can be modeled, lots of ways to do this one. So the next three are actually pollution, or the next two are actually pollution removal ideas. And the second one is really just about nitrogen. So the pollutant is nitrogen, in-stream denitrification. The third one is floodplain reconnection. This could also reduce peak flows and volume if you were looking to do so. And but that one's sediment, nitrogen, and phosphorus. Again, these protocols have been vetted through the Chesapeake Bay Tmdl, North Carolina, South Carolina, Georgia. States that aren't in Chesapeake Bay are also looking at stream restoration as a BMP. And my belief is Colorado needs to define these as well. So, and then the last one is dry channel or regenerative stormwater conveyances as a retrofit. So that's really retrofit and outfalls, and I'll get more into this in a minute. So let's get into it. Protocol 1. We all know that tremendous amount of sediment, and the case study I'll show will define this, that comes to our waterways is actually coming from the streams, rivers, and creeks themselves. So we have these massive eroding streams because of past land use activities, straightening, removing vegetation, change in urban hydrology, and it just causes these streams to start falling apart, and all this sediment ends up downstream and in the creek and pollution to the creek. So protocol 1 is creating the prevented sediment for storm flow. And this protocol has 3 steps. You estimate the stream sediment erosion rate and annual sediment loading. You convert the erosion rate to whatever nutrient you're concerned about. You could also do this for metals. And then you estimate the reduction attributed to the restoration. And again, there's lots of models out there, but you could actually go out and put pins in the bank, do some LiDAR surveying, however you want to do it, to estimate how much you've removed pre-construction and post-construction. Post-construction, certainly you don't get rid of all stream erosion, but you do get rid of somewhere, based on research and my own personal projects that I've actually gone out and physically measured things in, somewhere between 50 and 85% of stream bank sediment through restoration or bioengineering. So here's just some examples of some projects I've worked on where we've actually measured bank retreat. You see this bank was retreating so far, it moved over probably 50 feet and exposed the manhole and the sewer lines just underneath. We picked that up and moved it back. And then here's some before and afters of some severe erosion happening in a suburban environment. The second protocol is denitrification. And there's a lot of research that's been put into this. This is a lot in the Midwest is going on with this. And what we've learned is this interaction of groundwater and surface water, and basically the temperature change creates a denitrification zone. And that's called the hyporetic zone in stream terms, but that doesn't really matter what you call it. What's happening is the mixing of the water between surface water and groundwater and the movement of water through the sediments. So similar to some of the processes that we have when we build a sand filter or a bioretention basin or a rain garden, that same processes are removing nitrogen in the stream. So you think of all the streams we've lost in our urban environments, and especially those ephemeral streams, which are more sandy in nature. We've really eliminated, miles and miles, hundreds of miles of sand filters across our country and BMP. So we need to protect this and recognize the value of this zone. So, your stream design can really influence this denitrification. Having a lot of bed depth diversity, pools and ripples will help create that good mixing zones between groundwater and surface water in perennial systems. So, here's just some examples of, simple boulder ripples, rock ripples, brush tows, log sills, rock and roll ripples, which is a mix of boulders and logs, veins, anything that creates depth variability where you create some of that deep, cool water. Anybody who's done some trout fishing knows deep, cool water is where the trout like to go. Third protocol is floodplain reconnection. A lot of stream restoration revolves around either bringing the stream up to the floodplain or creating a new floodplain at a lower elevation if you're in an urban environment where you're worried about flooding. But that connection into that floodplain creates a lot of pollutant removal benefits. One, it can reduce downstream volumes, downstream peaks. This presentation is not about that, but certainly that's a huge benefit. And then you have all that infiltration by storage. Water will go back into the groundwater and slowly come back into the stream. You have vegetation uptick. You have wetlands out in a lot of floodplains. So just good thing. This example is moving the stream over to recreating a priority wine restoration where you backfill the old stream and put the new stream back in the old valley. And the next picture is just simply filling with some buried grade control, boulder grade control in here, but just filling the stream back up and reconnecting it with the floodplain, and then also a little bit of grading to bring down some of the floodplain. And so the protocol here as far as process, again, if you want to deep dive into this, you're welcome to review the paper that I referenced. I can provide you a link too if you contact me. But step one is you estimate the floodplain connection volume. This can be done through gauges out on your site, or you can model it. Step two is estimate the nitrogen and phosphorus removal rate. So some states are using some of the wetland, like stormwater wetland data to sort of estimate these. If the floodplain is more of a wetland, others are using measured rates based on volume. This is actually out of that paper and provides the annual total suspended solid removal rate based on rainfall and storm event. Or storage volume and storm event, sorry. So then you compute the nitrogen, phosphorus, or other pollutants of concern delivered to the project, and then how much was removed by that floodplain connection. So no different than any other BMP in how you're calculating volume in, what's the loading in that volume, and then what's the removal rate of the BMP, this BMP being the floodplain, and then what's the outcome of that. Again, we want to be able to compare stream restoration to detention ponds, to full spectrum detention, to rain gardens, so we can decide what's the best use of money in a community and how can we best make more livable and safe cities. Protocol 4 is really just about cleaning up your outfalls as part of stream restoration projects. So this is almost becoming a standalone practice, but typically when you're doing stream restoration is a great chance to connect the outfalls across the floodplain, maybe get rid of some point discharges, create a little overland flow, or get rid of a lot of these. As we all know, a lot of times where you have a ditch or a pipe coming into a floodplain, you have a big head cut, erosion, and so turning that on the picture on the left to this picture on the right, and then creating some wetlands and reconnected floodplain that we talked about earlier. And then so you have both the preventative sediment you can take credit for and some treatment train ideas. Here's one I designed. Again, going back to streams create happiness and joy. This is one I designed in the downtown park of Atlanta, Georgia. It's an Olmsted park, same father of landscape architect, also designed Central Park in New York City. We did a bunch of restoration in this park, so I definitely had to look awesome and look natural. So here's an RSC that's during a storm event. Here's during a dry, where people really love it. I've never seen anybody take engagement photos in a extended detention pond, but these are floodplains and stream restoration projects. People think they're natural, and they're at the top of the photo. You can actually see us nerdy engineers see that that's like a 48-inch pipe outfalling, and then they're standing just above the creek, as you can see in the reflection. So anyway, really cool to be parts of these types of projects, make our communities better, make them more livable, make them bring some joy and happiness into those communities. And you can figure out how much pollution you're removing with that. So during a low flow, this acts more like a sand filter with it flowing through. During high flow, it acts like any other boulder step pool, but it gets rid of all that grout and other things that could actually add pollution into our streams through algae, pollution through temperature, and creates a BMP, which is more like a sand filter or bioretention basin. These are meant to be no maintenance, or at a minimum, very low maintenance outfalls. Here's another example where the outfall is not a big step down, but it's just coming in and causing big ugly eyesore. Obviously the trees were denuded. This is at the very beginning of construction, end of a road, typical outfall into a dry channel here. and then just turn that into basically a big bioretention, zero maintenance bioretention style basin where, built the boulder seal. I'm standing on the pipe, or the photo is being taken from the pipe. And, you see the mulch and other things that come in just like a rain garden, but a rain garden that's not going to be maintained. It's just going to kind of self-naturalize and become part of the system. And then also this larger stormwater outfall can access it during flood events. So this thing has treatment for that little pipe you saw in the before picture and treatment for the larger channel that it's part of. So let's talk about a case study. This is a project, and this goes well beyond. So that paper I showed you before, the protocols, was 2014. This is something I've spent the last 13 years working on, implementing projects that came out of this plan, helping restore 7 to 10 miles of stream there. So this is a Tmdl avoidance plan. So a Tmdl avoidance plan is an EPA Category 4B plan so that a community can avoid a Tmdl. So EPA was going to give Charlotte-Mecklenburg, that's the city of Charlotte Skyline, a Tmdl for sediment, nitrogen, phosphorus, and biological integrity for this watershed. And they said, we will fix it ourselves. We'll come up with our own plan. So they moved from being a passenger on EPA's bus as an MS4 to driving the bus themselves. So, this is the cove. This is the drinking water supply of 1.5 million people. So there's the raw water intake. So this is a big deal lake. And this is actually EPA. So when EPA comes out and wants to kayak this area, and they come into the cove of the lake that it feeds into, which again is a drinking water lake, and they're in this much sediment, you probably know a Tmdl is coming. There it is in just the Google Earth aerial I pulled pre-2008. So here's the data. So here's what's in the plan. So where's all that sediment coming from? So it's coming from one cove. That whole lake sediment is coming from one cove. And that cove is a drainage area that comprises only 15% of the total drainage area of that lake. So the total lake area probably is about 2,000 square miles. And this watershed's about 30 of that. So very small percentage, but the 89 or almost 90% of the sediment in the lake is coming from this one watershed. So a fixable problem is the good news. So it was estimated that there's 50,000 tons of sediment coming into Lake Wiley's the name of the lake, into Lake Wiley, and that sediment's coming from 3 sources. Large streams, which are the major streams, about 15,000 tons per year. Minor systems, which are streams smaller than 1 square mile in draining area. So to equate that to Colorado, that's going to be about a 10-foot wide stream. And there's about 30,000 tons there. And then upland sources, right? So sediment from bad construction management habits, sediment just running off parking lots, but that's a pretty small percentage. So if you're going to reduce the sediment, and they wanted to reduce the sediment to avoid the Tmdl by 45,000 tons, what do you need to do? Well, you obviously need to address the sediment that's coming out of the streams from the minor systems and the major systems, and maybe do a little bit in the upland, take some low-hanging fruit. Okay, well, what does that mean? And just before I get into sort of some of the costing, again, this is a 2008 study, and these are some of the projects that came out of that have been a decade. So there's 70 miles of streams with a 50 square mile or greater drainage area in this watershed. And the goal, they thought they could reduce most of the sediment by restoring somewhere between 10 and 15 miles. So again, remember we talked about a 2,000 square mile watershed, and then we broke down the problems actually coming from 30 square miles. And then in that 30 square miles, it's about 10% of the streams to 15% of the streams that are just dumping a ton of bed sediment from bank erosion. So you see these picture dates are 2012. So these projects have quite a bit of data on them. And that's me holding a survey rod and me walking channels, doing banks modeling. So again, what is this going to cost? So we wanted to understand what typical BMPs, and most of these BMPs would only treat uplands, right? And that's what we think about. We want to remove sediment. Well, we need sand filters. We need wet ponds. We need wetlands. We need rain gardens. We need extended detention. We need pond retrofits. Well, what's the cost of that? And again, there's only a small percentage coming from uplands. And this is, again, $2,008. So you're somewhere between $70 a pound, $70 per pound of TSS removed to do that for extended detention. Or, the cheapest thing was a filter strip or sorry, a water quality swale, so just a simple grass swale, for about just under $4. So how does that compare if we were just to do stream restoration? Again, these are 2008 dollars. These have significantly gone up, but still everything would go up together. And you see, you can remove a cost per pound of sediment removed for somewhere around $1.50 to $2 a pound at $300 a linear foot. So that's what they decided to do. They decided in 2008, we're going to go all in on stream restoration to, again, protect the drinking water of 1.5 million people and keep this stream from getting on the Tmdl list. And we're gonna measure it, we're gonna quantify it, and we're gonna monitor it. So here's some of the project photos, some of the stuff going on, befores and afters, some of the streams. So you can see, big drastic changes. You don't see any of that mass bank wasting anymore. You see much more improved habitat for fish. They are measuring fish communities in here, benthics, and then have a sediment gauge or water quality gauge that measures sediment and other nutrients at the downstream end. So they're really monitoring this. More pictures, some different types of structures, logs, things. And again, this was pre the paper, so all they really took credit for was Protocol 1, which was just preventative sediment. But if we went back, you could also take credit for floodplain connectivity, denitrification in the hyperag zone, and some RSCs, regenerative stormwater conveyances, we put at a lot of the outfalls. So we didn't even quantify that, but again, this is Tmdl avoidance. So here's the picture I showed at the beginning of this case study, and this was pre-2008, and I just pulled this one down from Google Earth, so you see the drastic thing. Obviously, these, a lot has to do with when the photo's taken relative to rain and runoff, so don't think it's this clear all the time. But it has made a significant difference. About 10 miles of restoration has solved a giant problem that was going to be, tens of millions of dollars of treatment plant upgrades. The raw water intake somewhere in here, again, serves over Charlotte, Mecklenburg County, well over 1 million people get their drinking water from here. But the coolest thing about stream restoration, again, is yes, let's measure how much sediment we're reducing, how much nitrogen we're reducing, how much phosphorus we're doing, how much peak flow we're shaving, how much volume we're reducing. But we also, with stream restoration, bring a lot of joy and happiness. That's happened in the projects I worked on in Charlotte. The community's really gotten behind them. There's a line of HOAs and other neighborhoods that now want to have projects in their backyards, urban areas, which are doing a lot of projects. But in Denver too, these pictures are all taken along the Platte on the right, and people really enjoy streams as an amenity. In the 50s, 60s, 70s, and maybe in the 80s, we only thought of streams as liability, right? We put sewage in them, we put pollution in them from industry, they stunk, they were a nightmare, they flooded us, they killed people, streams were bad, streams are bad, they're a liability. I think now as a society we realize the value of those ecosystems, the value of those amenities in our urban cores, in our urban environments, and streams have moved from a liability to an asset. And there's me and my wife on a hike, and water brings us a lot of joy, and I've had a great career helping restore ecosystems and streams all over the United States, and I'm happy to be here now in Colorado. So anyway, thank you for attending my presentation, and I'll end it there.